Here I want to look at type checking when we have type classes involved. One of the simplest examples of this is the member function, which takes a list of items and an item and tells us whether that item belongs to the list or not. So you might think that the type of this would be list of A to bool. But the point is you can't apply member to elements of any type whatever. It needs to be a type on which there is an equality function. So we need A to be a member of the equality type class. And we express that in the type by putting EQA and then this fat arrow. And that's called the context. So we have the constraints on the type variables go into the context. And the constraint here is that A is in the equality type. We use equality over that type. Now let's look what happens when we apply that function to an expression E, which is a list of B, but where we're assuming the things in B are ordered. So ord B sits there before the fat arrow saying B belongs to the ord type class. And so how do we type check this? We're applying member to E, or you have to unify the input type list of A with the type of E, which is list of B. So that gives us this type for member, where we've replaced A by list of B. And when we make the application, we get a function back of type list of B to bool. But what do we have in the context? We have ord B in the context from the type of E, but we also have EQ of list of B in the context because of the member function itself. So now we've got a context that's requiring two things. It's requiring equality on list of B, and it's requiring an ordering on B itself. Now we could leave that context as it is, but there are two different ways we can simplify it. The first simplification we can make is to replace equality on list of B by equality on B. Now, why can we do that? Well, because the instance declaration says there is an instance of equality on list of A if there's already an equality on A. So we can replace. We know we've got an equality on lists if we got equality on the individual elements. So let's replace the equality on list of B by equality on B. So that instance declaration allows us to replace one thing by another. But we can also get rid of that equality on B completely, because the definition of the class of ordering says in order to be in the order class, you have already to be in the equality class. So if we know ord B, then that means EQ of B must be true already. So we don't have to worry about EQ of B. So in fact, we can simplify this so that all we require is that B is ordered and we have a function from list of B to bool. So we've simplified the context using instance declarations, replacing the thing on the right by the thing on the left, and class declarations where we've been able to eliminate the thing on the left by the thing on the right. So they go different ways around it, but that's because one is an instance declaration, one is a class declaration, and they're doing quite different things. So that brings us to the end of type checking of polymorphic functions. We've seen how it applies to, first of all, we've seen how it applies to monomorphic functions. Then we saw how unification comes in to deal with function application of polymorphic functions. And now we've seen something about what happens in the presence of type classes, where we still perform unification, but we also do simplification of the context.